In this video, we'll talk about AVL tree insertion. So there are other videos which are related to AVL tree deletion, which are also uploaded to my channel. So let us look at first the motivation behind coming to AVL trees or learning about AVL trees is usually we build binary search trees so that searching is faster for us. What do I mean by that is, we know that linked lists, we have two data structures, that is we have arrays and we have linked lists. In arrays, the memory allocated, the memory which is allocated should be defined at the beginning of your program, and index usually starts from 0 here, and name of the array must obviously be given, and accessing array elements is using the index numbers from a of 0 to a of n-1, where n is the size of your array. The problem here is, once you have defined the size of the array in your program, throughout the program the size remains same. Increasing the size or decreasing the size of the array is not possible for us. That is, throughout your program, if you have declared the size of your array as 500 and you only use 5 memory locations in that throughout your program, then other 495 memory locations are allocated but not used, and that 495 free memory locations cannot be used by the other programs. So this is a wastage of memory for us, so and not a good programming practice and not a good way of implementing the array data structure. Another thing is, size cannot be increased or reduced. Size has to be declared at the compile time itself. That is, your compiler should know what is the size of the array before it starts working on the arrays. And searching an element, so suppose for example, if you have 5, 6, 7, 8, 9, these are the elements which are stored, and if you delete the element 7, obviously there is a gap left off here. So what you have to do is, you have to shift all the elements 1 to the right hand side, so the resultant array will be 5, 6, 8 and 9. So you have to shift the remaining elements one step to the back side. So this is a little bit of tedious task for us. Okay, that is, everything is static in nature when it comes to arrays, whether it is size or whether it is elements, movement of array, movement of elements, and so on and so forth. So everything is static in nature and everything is cumbersome for us once we start using this. And to avoid all those things, we talked about linked list, where we said that we create a node during the runtime as and when it is required, and the nodes are arranged in such a way that every node remembers the address of the next node, and so on. And we then talked about doubly linked list, where every node remembers the address of next node and previous node. And then we talked about doubly circular linked list, where first node is attached to the last node. So this is useful in a way that if you want to reach the last node directly, you can reach it. It can be traversed in all the ways. Okay, and the memory, as we are allocating the memory dynamically as and when it is required, so there is no wastage of memory also. And if you want to delete a node, the memory can also be deleted. So this is way more advantageous when compared to an array. But the problem is, if you want to search for an element, whether in a linked list or whether in an array, what happens is, suppose if you are searching for an element, we are talking about worst case. If you want to search for an element 8, you have to compare whether, you have to check whether 5 is equal to 8, 6 is equal to 8, 7 is equal to 8, 8 equal to element has been found. So you required 4 comparisons. The same happens with your linked list also. The same happens with your arrays also. 4 comparisons are required. That is, you have to check whether first is the 8, second is 8, or third is 8, fourth one is 8. You stop here. So 4 comparisons. So here searching for an element is little bit a cumbersome process, where you have to check each and every element in the list or in the array or in a linked list to check whether to find an element. and also finding minimum and maximum becomes cumbersome. That is, if you want to find the maximum element in an array, you assume 5 as your minimum element, and if 5 is less than 6, you say that increment the value. So then you check 5 with 7, then you check 5 with 8. Only after checking 5 with all the other n-1 elements, you say that 5 is lesser than n-1 element. So n-1 comparisons are required. Same with your linked list also, n-1 comparisons will be required for us. So even though when it comes to memory usage, when it comes to memory allocations, linked lists are better when compared to arrays. And also insertion deletion also becomes easier once the memory is dynamic and once memory is flexible, but finding minimum and finding maximum, searching for an element is still the same as an array. So to avoid this, we change the linked list, or we implement the linked list in a different way. So we say that we come to the concept of binary trees. We just modify the linked list concept and we talk about binary search trees, where we'll organize the nodes in this order. So this stores address of 4, this stores address of 3, and you'll be having 6 here. So we just modify the linked list data structure, double linked list data structure, in such a way that it looks like a tree for us in upward direction, okay, reverse direction, and we organize the data in such a way that all the elements, so we call this as a root node. All the elements less than the root node will be on the left hand side, and all the elements greater than or equal to the root will be on the right hand side. So we organize it in this way. So the advantage of having this kind of arrangement of your linked list and this tree kind of structure is, suppose if you want to find a minimum element will be the last element on the right hand side, and maximum element will be the last element on the minimum element will be last element on the left hand side, and maximum element will be the last element on the right hand side. So if you move towards the last element on the right hand side, you get the maximum element. If you move towards the rightmost element on the right hand side, you get the minimum element. So minimum and maximum comparisons gets reduced in a binary search tree. And also we have talked about binary search trees in other videos. But the problem arises when, suppose if you want to store 5, 6, 7, 8, and if you want to build a binary search tree out of it. So tree is built in this way. So this is your root. Now this is same as any linked list for you, so on, and it is also same as any array for you. So once you have this kind of elements and your tree is looks like a linked list or an array, it also inherits the properties of linked list and arrays, because to search an element 8 you have to go through all the n-1 elements. You have to search for all the n-1 elements. So the same properties of a linked list and same problems we have discussed previously comes here. So we kind of have to avoid such kind of situations. That is, whenever we have a sorted numbers, so what happens is and they are consecutive in nature, we get such kind of trees. So if you have suppose for example 5, 4, 3, so you get a tree of this form. So such kind of trees must be avoided. So for this, what do we do is we apply some kind of balancing here, and that balanced binary search trees are nothing but your AVL tree. So an AVL tree is a balanced binary search tree. Okay, we'll look at how this balancing can be applied. Consider this example. We'll try to understand this concept with an example here. So first element comes, we create a node and we call it as a root. Elements are inserted, so insertion takes place same as your binary search tree, and we calculate a parameter called as balancing factor for every node. and this balancing factor, if it is 0, 1 or minus 1, then we don't have any problem. If it is anything apart from that, we'll see what has to be done. So here the balancing factor of this node is 0 because you don't have any levels on the left hand side of it and you don't have any levels on the right hand side of it. So balancing factor of any node is calculated as height of the left subtree minus height of the right subtree. So what is the height of the left subtree? You don't have any tree at all on the left side, you don't have any tree at all on the right hand side. So that is why the balancing factor is 0. 0 minus 0 is 0. Next element is 2 for us. So 2 is greater than 1. 2 comes to the right hand side of the root. Now if you calculate the balancing factor here, so we always start by calculating the balancing factor from the root. So balancing factor of this element is height of the left subtree. You don't have any levels to the left hand side, you don't have any levels on the right hand side. So 0 minus 0 is 0 for us. And the height and the balancing factor of this node changes because you don't have any levels on the left hand side, but you have one level on the right hand side. So 0 minus 1. Okay, you have 0 levels and you have one level. So 0 minus 1 is minus 1. So the balancing factor is minus 1 for this node now. So as you can see, if the balancing factor is 0, 1 or minus 1, we don't have any problem at all. Next element is 3. 3 is greater than 1, 3 is greater than 2, so 3 is placed here. Now calculate the balancing factors. Balancing factor of this node is 0. Balancing factor of this node is minus 1 because 0 levels on the left hand side and 1 level on the right hand side. 0 minus 1 is minus 1. And balancing factor of this node is 0 levels on the left hand side and you have 2 levels on the right hand side. So 0 minus 2 is minus 2. So now we have got an imbalance. So on node 1 we have imbalance, that is on node 1 we have an imbalance called minus 2. That is the balancing factor is anything apart from 0, 1 or minus 1, then an imbalance has been occurred. So whenever an imbalance occurs, rotation should take place. So there are different types of rotations: RR, LL, RL and LR. So there are different types of rotations: right, left, right, left, right, which has to take place. Let us see what are these rotations, and after applying these rotations your tree will be balanced. That is, we will not be getting such kind of trees here. So we start from the node where the imbalance has occurred. So with respect to this node, so imbalance has occurred here. So with respect to this node, where is the new element inserted? Because after inserting the new element, the imbalance has occurred, right? So with respect to this node, where the new element is inserted? So new element is inserted to the right side of 1. So write 1 R here. To the immediate child node of 1, where is the new node inserted? The new node inserted to the right side of immediate child node of 1. Write another R. See, imbalance has occurred here. You always start from the node where the imbalance has occurred. So with respect to the imbalanced node, new node is inserted to the right side of 1, that is the right side of imbalanced node. You write 1 R and come to the immediate right side of element 1. So with respect to the immediate right hand side node of your imbalanced node, where is the new node inserted? To the right side of it. So write another R. So this is RR imbalance for you. Whenever RR imbalance occurs, you pull the element between both the R's above. So when you pull an element below both the R's, so 1 falls onto the left hand side, 3 comes onto the right hand side, root becomes the parent. So the resultant tree will be 2, 1, 3. Now look at the balancing factors. So the balancing factor of all the nodes is 0, 0. This is also 0 because you have one level on the left hand side, one level on the right hand side. So 1 minus 1 is 0. So tree is balanced. So we have avoided such kind of trees, okay, where such kind of trees inherits the properties of linked lists and arrays. So this is what we mean by rotations. So similarly, take another example. Insert another element. So you want to insert element called 4. 4 is greater than 2 and also 4 is greater than 3. Calculate the balancing factors for it. So this is 0. So 0 minus 1 is minus 1. So you have one level here and you have 2 levels here. So 1 minus 2 is minus 1 for us. No problem, because if balancing factor is 0, 1 minus 1, now that is whenever such kind of trees occur, we try to push some nodes onto the left hand side, onto the right hand side, or onto the right hand side. Okay, when you have more than 2 levels and you don't have any levels on the left hand side or right hand side, you try to adjust them by moving to the left or right. Okay, that is what is your rotation means. Another element, so the element 5 has to be inserted. 5 is greater than 2, 5 is greater than 3, and 5 also 5 is greater than 4. So now calculate the balancing factor. So balancing factor of this node is 0, balancing factor of this node is -1, of this node is -2. Wherever the imbalance occurs, you stop. So 0 levels and 2 levels, 0 minus 2 is -2. So with respect to this imbalanced node, the new node is inserted on the right hand side. With respect to this immediate right hand side node of the imbalanced node, which is 4, the new element is inserted to the right hand side of 4. So this is again RR imbalance for us. So whenever RR imbalance occurs, you just pull the element between both the R's. So whenever rotation applies, whenever you pull element 4 above, only one level above 4 and one level below 4 will be affected. Rest of the elements will be same for us. Okay, so when this happens, 2 and 1 are same. So when 4 is pulled up, what will happen is 3 falls onto the left hand side and 4 becomes the parent node. So you have 4, then you have 3, then you have 5. So calculate the balancing factor: 0, 0, 0, 0, 1 level and 2 levels. So 1 minus 2 is -1. So tree is balanced for us. Okay, so let us take another. So you have 2, 1, 4, 3 and 5. This is the node. Now we want to insert element 6. 6 is greater than 2, 6 is greater than 4, and 6 is greater than 5. Calculate the balancing factor here. So you have 0, this is -1, 1 minus 2 is -1, that is 1 level, 1, 2, 2 levels. So 1 minus 2 is -1, this is 0, 1 level here, 1, 2, 3, 3 levels, 1 minus 3 is -2. So again you have a imbalance. So with respect to the imbalanced node, the new node, which is 6, is inserted to the right side of it. With respect to its immediate child node, that is 4, which is immediate right side of 2, the new node is inserted to the right side of it. Okay, 6 is inserted to the right side of 4, so write another R. So this is again RR imbalance. You pull element between both the R's. So 2 comes and falls onto the left hand side. So 4 becomes new root. So you have 4, 5, 6 are same for us. Now what happens is when 2 comes onto the left hand side, what will happen is 2 becomes the left hand side branch of 4. So previously there was 3, for now ignore the element 3, so 2 becomes the new left hand side. So 2, for 2, 1 is attached to me. But here at this point element 3 was available, which was occupied by the element 2. So what you do is you take the element 3 and compare it with 2. So if it is greater than 2, you insert it onto the right hand side of 2. If it is less than 2, insert it onto the left side of 2. So obviously it will be greater than 2, so you insert 3 to the right side of 2 here. That is, whenever a rotation applies, 2 occupies the place of 4. Okay, now what will occupy the place of 3, and 3 will be compared with the element 2. If 3 is greater than 2, it comes on to the right hand side of 2. If it is less than 2, it comes on to the left side of 2. Okay, so this is about RR rotation. So similar kind of thing can also be applied for LL rotation. Suppose for example you have 5, 4, 3 and 2. So 5 is the root node for you, 4 is less than 5, no problem. So the balancing factor is 0, 1 minus 2 is 0, 1. So next element is 3. So now when imbalance occurs, that is 0 and this becomes 1, that is 1 minus 0 is 1. Now here it becomes 2, that is 1 to 2 levels, minus 0 is 2. Imbalance has occurred. So with respect to the imbalanced node, the new node is inserted to the left hand side, and with respect to the immediate left hand side of the node, imbalanced node, the new node is inserted to the left hand side. So whenever LL imbalance occurs, similar to RR, you pull the middlemost element between both the L's. So when 4 is pulled, 5 becomes the right side of 4. So you have 4, 5 and 3. Okay, so this is your LL imbalance. So RR and LL imbalances are covered for us. Okay, now for now, remember this a trick which will help you in solving the problems. Suppose if you have a node A, B and C of this form, and an imbalance has occurred and you are asked to apply rotation. So here what you do is, you suppose, let us take a real example. Suppose you have 6 and you have element 8. So this is your tree, and element 7 is inserted. So 7 is greater than 6 and 7 is less than 8. 7 gets inserted here. Now let's calculate the balancing factors. 0, 1 minus 0 is 1, 0 minus 2 is minus 2 for us. So with respect to this imbalanced node, so minus 2 is, so anything apart from 0, 1 or minus 1 is imbalanced for us. So with respect to this imbalanced node, the new node is inserted to the, that is new node which is 7, is inserted to the right side of 6. With respect to the immediate right hand side, where the element 7 is inserted to the left hand side. So this is your RL imbalance. Whenever RL imbalance occurs, assume this as ABC, C becomes your root, okay, and then A becomes your left hand side and B becomes your right hand side of it. That is, if you assume this as your A, this as your B, and this as your C, and such type of situation occurs whenever in your program, you can directly write it as 7, 6 and 8. Similarly, if you have 5 and if you have 3, your root, and element 4 has to be inserted. So 4 is less than 5 and 4 is greater than 3. Now let us look at what type of imbalance you have here. This is 0, 0 minus 0. So 0 minus 1 is minus 1. This is 2 for us, that is 2 levels here and 0 levels here. 1, 2 levels, and here 0 levels. 2 minus 0 is 2. Imbalance has occurred. So with respect to the imbalance node, new node which is 4 is inserted to the left hand side. With respect to this immediate left hand side node, the new node is inserted to the right hand side. So you have LR imbalance. Whenever you have LR imbalance, write them as ABC, and you write it as C, B and A. So this will be your C, this will be your B, sorry, this is your A, B and C. So what happens is, if you apply CBA, so it will be 4, 3 and 5. Okay, so that is for your LR, it will be C, B and A. If this is the case, that is if A, B and C is the case, and for RL it will be C, A, B, that is if you have such kind of case, A, B and C. Okay, if you remember this, it will be much easier for you in the forthcoming, in next examples which we will be seeing. Let us take an example. Let us take a big example and try to solve that. So 5, 4, 3, 1, 2, minus 1, minus 2, 11. So let us assume these are the elements which are given to you. You insert 5, no problem. You insert 4, 4 is less than 5, so 4 comes here. So till here no imbalance, that is, you imbalance factor is 0 here, imbalance factor is 1 here. Okay, 1 minus 0 is 1. Next you insert 3. Now what happens is, imbalance factor here is 0, 1 and 2. So that is 1 minus 0 is 1, 2 minus 0 is 2 for you. So with respect to this imbalance node, element 3 which is new node is inserted to the left hand side of it. To its immediate left hand side node, the new node which is 3 is inserted to the left side of it. So it is an LL imbalance. You pull the element between both the L's. So 5 comes and falls to the right hand side of 4. So you have 4, 3, 5. Okay, so let us assume that this is your 12 and this is 19. So next element to be inserted is 19. 19 is greater than 4 and 19 is greater than 5. 19 comes here. So tree is balanced here. 0, this is minus 1. This is, so this is your 0. This is minus 1. So this is 0. 1 minus 2 is minus 1 for you. Next you insert the element 12. So 12 is greater than 4, 12 is greater than 5 and 12 is less than 19. So 12 comes here. Calculate the balancing factor now. This is 0. This is 1, that is 1 minus 0 is 1. Next here what is your imbalancing factor? 0 minus 2, which is minus 2. So imbalance has occurred. Stop here. Don't calculate for any other nodes. So here this is a kind of this situation, ABC condition, that is RL situation, that is imbalance has occurred here. With respect to this imbalanced node, new node which is 2L is inserted to the right hand side of it. With respect to its immediate right hand side node, the new node is inserted to the left hand side, RL imbalance. So this is your A, B and C. In your RL imbalance, what do? You write it as C, A and P. So now what happens is, whenever rotation happens, only one level, only those nodes which are interconnected and which are related to the imbalance will be changed for us. So what will happen is 4 and 3 will be same for us. So ABC becomes, C is the root parent node for you, 12, and A comes onto the left hand side and B comes onto the right hand side. So this is your RL imbalance. Suppose let us assume you want to insert another element which is 20. So 20 is greater than 4, 20 is greater than 12 and 20 is greater than 19. So 20 comes here. Calculate the balancing factors. 0, minus 1, 0, 1 minus 2 is minus 1. This is 0, 1 minus 2, minus 3 is minus 2. So imbalance has occurred here. So if this imbalance has occurred, what do we do is, with respect to the imbalance node, new node is 20 which is inserted to the right side of the imbalance node. With respect to its immediate right hand side, the new node 20 is also inserted to the right side of immediate 12. So it's an RR imbalance. Whenever RR imbalance occurs, you pull the element between both the R's. So what will happen is 4 comes to the left hand side of 12. So you will be having 12, 19, 20. All the same is same. All the nodes are same. 4 comes and occupies left hand side, that is 4. 2, 4, 3 is attached. No modification. But only thing is, in place of 5, 4 occupied the position of 5. So what do you do is, you compare 5 with 4. So 5 is greater than 4. So 5 will be placed onto the right hand side for you. Okay. So this is the tree which we will be obtaining. Okay. So that's about AVL tree insertion. We'll talk about more examples in forthcoming videos. We'll talk about some more examples and other topics also.